Okay, in this video, we're going to be looking at finishing up chapter 4 and considering section 6 on optimization. Okay, in this section, like I said, we're going to work with optimization, and basically optimization just means we want to learn how to optimize certain quantities, and that means finding maximums or minimums of functions. And yes, these will be word problems, but we're going to more often than not, we're specifically looking at business applications. I am going to start with just a basic geometric example and then lead into the business applications. Okay, so here's our first problem that we're going to look at, and I'm going to kind of pull up the steps here on the slide and kind of work along with those. So the question is, what are the dimensions of a rectangle that has an area of 225 square feet and it has the least perimeter? So on these, what's going to happen is you're going to see where you're asked to find like the largest perimeter, the smallest perimeter, it's going to be the greatest or the least on all of these that you're looking for. And so that's the optimization part of it. So if we look at this, we've got a rectangle here, and I'm going to sketch it out so you can kind of follow along with me on this. Okay, so we have a rectangle. It has an area of 225 feet. So if you remember, square feet that is. So if you remember from geometry, area of a rectangle is length times width. So the length times the width is equal to 225 square feet. Okay, and we can also come up with a perimeter equation. If this is our length and this is our width, perimeter is basically like if I was to put a fence around this, how far would the fence need to be? So this side would also be my width and this would be my length. So I have two widths and two lengths, and those two together give me the perimeter. Okay, so in a lot of these problems, we're going to have two different equations. One equation is what we want to minimize or maximize. The other equation relates the two variables that we have. So here we have an area equation and we have a perimeter equation. Okay, so what we're going to do is we're going to solve one of the equations so that we can make a substitution into the other one. So we want to start with the one that's not the one that we're going to be minimizing or maximizing. So we're asked to find the least perimeter. That means we need to minimize the perimeter. Okay, so I'm going to start with the area function here. So area we know is length times width is 225. Okay, so I'm going to solve this. It doesn't really matter whether I solve it for length or width. The slide here is solving it for the length, so I'm going to solve it for the length as well. So that means I'm going to just divide by this W so that those will cancel. And so the length is 225 divided by W. So what that does is it's going to allow us to take this and substitute back into this equation of the quantity that we want to minimize, and then we'll be able to proceed from there. So my perimeter then is going to be 2W plus 2. In the place of this length, I'm going to substitute what I just found the length to be. So the length is 225 over W. Okay, so we'll simplify this as much as we can. So 225 times 2 is going to be 450 over W. Okay, so we want to use one equation to solve for one of the variables and substitute into the equation that we want to minimize or maximize. So now we have the perimeter in terms of just a single variable. What we want to do next, because we want to find the least perimeter or minimize it, is we know that to find a minimum, you do that by taking the derivative. So we're going to take the derivative of this quantity here, and before we take its derivative, I do want to rewrite this and bring that W up as a negative exponent. So the derivative then is going to be 2 plus, remember, multiply those two together, so negative 450 w to the negative 2, because we'll decrease the power by 1. So we'll have 2 minus 450 over w. That would be over w squared. All right, we're going to take our derivative here, which we had written as this, and that's the same thing as what's on the slide. So if yours is in this order, that's fine. If you recall from our previous sections, in order to minimize or maximize something, we always have to set it equal to 0. So that's what we're going to do here, is set this derivative equal to 0 to come up with our critical values or critical numbers for this. So I'm going to move this to the other side, so 450 over w squared, move that over so it becomes positive. So I'm going to cross multiply at this point, and then I'm going to divide by the 2. So I'm going to have w squared is equal to 225. So I'll take the square root. So w is going to be either plus or minus 15, because 15 squared is 225. Okay, we have to keep in mind that we're talking about sides. The w stands for the width of that rectangle that we originally started with. So we can't have a negative width. So our w, our critical number would just be the 15. Okay, so we have to decide from this if w equals 15, if that is actually a maximum or a minimum or neither. And the second derivative test can let us determine that. So we said our first derivative was 2 minus 450 over w squared. Okay, so I'm going to rewrite this as minus 450 over w to the negative 2. So if I take the second derivative of 2 is just 0. Here, if I multiply negative 2 times negative 450, I'm going to have 900 w to the negative 3, which will be 900 over w to the third, which is where they're coming up with this. So we want to evaluate the second derivative at that critical number of 15. Okay, and so this is definitely a positive number. So if my second derivative is positive, that means my function is concave up. So what I've shown here is that I do in fact have a minimum that's occurring at x equals 15. Okay, on these problems, we definitely want to make sure that we go back and look at what the question is actually asking once we've gone through this. So it's asking for the dimensions. So we know that our width is 15. We found that part out. But we also need to know the length. So the length, going back to here, is 225 over the width. So 225 over 15 gives me 15. So as it turns out, a 15-foot by 15-foot square is going to give is going to have an area of 225, but will have the least perimeter with that. So hopefully you can kind of get an idea of the steps. I know it's a little bit all over the place, but let's kind of recap here. We've got generally you'll have two equations of some type. So one equation is the one that you're going to minimize with the derivative, your critical numbers, and so forth. The other one is the one you're going to use to solve to make the substitution into the equation that you want to minimize or maximize. Okay, so this example leading into more business-related optimization problems, this one is on maximizing revenue and profit. So an office supply company sells X permanent markers each year at a price of P dollars per marker. Our price demand equation is P equals 10 minus 0.001x. So the question we want to address is, what price should the company charge for the markers to maximize revenue? Always read that question very carefully so you figure out what it is you're minimizing or maximizing. So we need in order to solve this, we need to maximize revenue. So in order to maximize revenue, I've got to first have a revenue equation. So if you remember from back previous sections, revenue is the number of units times the price, okay? So that's the equation that we want to maximize, but it's in terms of two variables at this point. That's where this second equation is going to come in. We want to make a substitution using this equation so that we can get rid of this p and have only x's as our variables. So I'm going to have this x and I'm going to substitute for this p. So in the place of p, I'm going to put 10 minus 0.001x. And I would distribute here just because it's going to be easier to take the derivative. Okay, so this is our revenue equation. But we haven't maximized it yet. We've just found out what the revenue equation is, but not what the maximum is. So in order to maximize it, we're going to have to take the derivative. So the derivative of 10x would be 10, and the derivative of this term here would be 0.002x. Okay, so that is our derivative that we're going to, in order to maximize it, we need to set it equal to 0 and find our critical numbers. Okay, so we are going to have some decimals that we're working with, but they're still not going to be, they're not going to be bad. Okay, I'm going to move the 10 to the other side here, so it's going to become a negative. And then I'm going to divide by this. So what I find is that x is going to be 5,000, okay? And x is the number of markers, so that's going to be 5,000 markers. Okay, we do need to check and see if this in fact gives us a maximum and not a minimum. So we can do that through our second derivative test. So the second derivative, I'm going to go back up here to the first derivative. Derivative of 10 is 0. The derivative of this term is negative 0.002. Okay, so since that is negative, that means it's opening downward. So I would have a maximum. Therefore, it's a maximum. So I have shown that, in fact, a maximum is occurring there. We want to make sure we answer the question that's being asked. So the question is, what price should they charge? All we've done is we figured out that the maximum revenue occurs when 5,000 markers are produced. We don't know what price to charge in selling those. So what we're going to do is we're going to take this price equation and figure out what price we need to charge when we're going to sell 5,000 markers. So that's going to be 10 minus 0.001 times 5,000. And so that's going to be $5 per marker. Okay, so this company needs to produce 5,000 markers in order to maximize their revenue, and the price that they need to charge per marker is going to be $5 per marker. Okay, the follow-up question then is, what would the maximum revenue actually be? Okay, so we found out that revenue, our equation for revenue on the previous screen was 10x minus 0.001x squared. Okay, so and we determined that the maximum revenue is going to occur when 5,000 markers are produced. So we're going to plug that in. And when I evaluate that, I'm going to get $25,000. Another way to think of it is our revenue is X times P. And we figured out that if we produce 5,000 units and we sell them for $5 a piece, that would give us our maximum revenue. So that is an alternative way to find that answer. Okay, here's a problem very similar to the one we just did for you to practice with. I would suggest pausing and trying it, but if you're not ready for that, then follow along here. Okay, so an office supply company this time sells heavy-duty paper shredders at P dollars per shredder. We have the price demand equation provided. So we're again looking for the price the company should charge for the shredders to maximize the revenue. So we need a revenue equation basically. So the revenue equation we know is X times P. So I'm going to use this secondary equation here and substitute in so that I don't have two variables. I only have one variable to work with. So I'll put in 300 minus x divided by 30. So when I simplify this, I'll have 300x minus x squared over 30. So that's my revenue equation. We know we want to maximize it. So as soon as I see that word maximize, I know I'm going to be taking a derivative. Okay, so the derivative of 300x is just 300. And then think of this as 1 over 30x squared. So I'm going to have the negative 1 over 30 and then times 2x. So 300 minus, that will be x over 15. Okay, once we've taken the derivative, we want to set that derivative equal to 0 in order to maximize it. Okay, so I'm going to move the 300 to the right-hand side. I'm going to move that over so it's going to become a negative. And then I'm going to cross multiply. So that'll be negative x is equal to 300 times 15 is going to be 4,500. And we'll divide by negative 1. I will say if you come up with negative numbers for answers on these, in a lot of cases you've done something wrong. You need to go back and check. So 4,500 in shredders is going to be the amount, the number of units that you want to produce in order to maximize the revenue for this. Okay, so we've got a couple of things we still need to do. We need to show that it is in fact a maximum, and then we need to find the price and the revenue with that. Okay, to show that it is a maximum, the second derivative is probably going to be the easiest thing to do with that. So the second derivative, okay, if I take the derivative of 300, that's just 0. Think of this one as negative 1/15 x. So the derivative of that would just be negative 1/15. That is less than 0, so it opens down and I have a maximum. Okay, so this does in fact give me a maximum value. So the price itself, I'm just going to substitute in for the lowercase p here. So 300 minus 4,500 over 30. So that's going to give us 150. So they're going to sell the heavy duty paper shredders for $150 in order to maximize the revenue. So our maximum revenue itself is going to be, our revenue is X times P. So we want to sell 4,500 shredders and we want to sell them for $150 a piece. And so we're going to generate, looks like $675,000 as our maximum revenue. Okay, this one's a little bit different because it deals with maximizing profit, not revenue. So we're going to kind of build from the example that we saw in example 1 and use some of that information that was provided to us. So we do know from that we found that the revenue was 10x minus 0.001x squared. So that's a carryover from example 1 that gave us that to work with. Okay, so when you read through this, they give us a cost function and they want us to maximize on the maximum profit. So I need to work with the profit equation and I need to take the derivative of the profit equation once I have the profit equation in terms of only one variable. So if you remember, profit is the revenue minus the cost. Okay, so the revenue was from example 1, and then the cost, and be sure you put the cost inside of a set of parentheses. So they give us the cost is 5,000 plus 2x. And I would say go ahead and simplify this as much as you can. It'll make it easier when you take the derivative. Okay, so I'm distributing the negative through. And then I'm going to combine some like terms. So the 10x and the 2x will give me 8x. And then the rest don't have like terms. Okay, so I have my profit equation. So the next step, just like we did with revenue, is we are going to take the derivative of our profit function because that is what we want to maximize. So the derivative of 8x would just be 8. The derivative here would be negative 0.002x. Then the derivative of the 5,000 is going to be 0. Okay, so we come up with our equation, we take the derivative of it, we set that equal to 0 in order to maximize it. So in this case, I'm going to move the 8 to the right-hand side. It'll become negative. And then let's divide this decimal away. And so x is going to be, if I divide this, I'm going to get 4,000 markers. Okay, so kind of in line with what we've done before, we want to figure out if in fact this is a maximum or a minimum. And that's where our second derivative test is going to become an important part here. So if I'm taking the derivative of the derivative to get my second derivative, the derivative of 8 is 0. The derivative here is negative 0.002. That's certainly less than 0, so it opens downward. So I do in fact have a maximum. So by doing this, I know that seems like insignificant, but it's really important because it tells us that this is in fact a maximum that you're working with. Okay, so we need to figure out both the maximum profit and the price to charge in finding that maximum profit. So our price, and again, this is a carryover back from the example 1 where they gave us our price equation. That's going to be 10 minus 0.001 times the 4,000. That's going to maximize it. So we want to charge $6 per marker. Okay, so our profit then, I'm going to go back over here to my profit equation. And I'm going to plug in the 4,000. So I'm going to have 8 times 4,000 minus 0.001 times 4,000 minus 5,000. And so my maximum profit is going to be $11,000. Okay. So kind of keep some perspective on this whole problem here. You're trying to maximize profit. So we want to work with the profit equation. And since we want to maximize it, we know to maximize something, we automatically have to take a derivative, set it equal to 0, and find our critical number. So that takes us down to here. So what we found is that by producing 4,000 markers, we will have our maximum profit. We don't know what we're going to charge for those until we plug it into the price equation, which is here. That gives us the price that we want to charge in order to have that maximum profit. And then we're going to plug that 4,000 into the profit equation to figure out what that maximum profit is. So there is a difference between the lowercase p and the uppercase. Uppercase is the profit. The lowercase is the price. Okay, here's one to practice. This goes back to the paper shredder example earlier, or paper shredder practice problem from earlier. And we're actually asked to maximize the profit again. It's so important that you're trying these. So I would say definitely pause it, get as far as you can, and then pick up with the video again. So from our previous example, we had determined that our revenue equation was 300x minus x squared over 30. Okay, so that means to find our profit equation, because we want to maximize profit. Okay, so I need a profit equation. I'm going to do the revenue minus the cost. Okay, and I do want to clean this up some before I take the derivative. So I'm going to distribute the negative through. Okay, and then we have some like terms we'll combine together. So 270x minus x squared over 30 minus the 90,000. That's going to be my profit equation. Okay, and we know from the steps we've already done that in order to maximize that, we're going to have to take the derivative. Okay, so the derivative here of the first term would be 270. The derivative of this one is going to be negative 1/30 times 2x, because just think of it as the fraction 1 over 30, and then the function is x squared. And then the derivative of this would be 0. Okay, so that's going to be 270 minus 2x over 30. We want to set that equal to 0, and you could do 1 over 15 here. That would be fine. Okay, so I'm going to have negative 2x over 30 is equal to negative 270. I'm going to divide by the negative 2 over 30. And so x is going to give me looks like 4050. Okay, and so that's going to be the number of paper shredders. That's going to actually maximize the profit. So it's possible to maximize revenue and not be maximizing profit, because you need to take into consideration that cost equation. So that's why your maximum profit may not occur where the maximum revenue occurs at. Okay, we do need to look at our second derivative in order to show that it is in fact a maximum. So if we go back to our first derivative, which is here, the derivative of 270 is 0, and the derivative here is just going to be negative 2 over 30 or negative 1 over 15. And so that's negative, so it opens down and we have a maximum. Okay, so this does in fact give us a maximum. The price, okay, is going to be P equals, and the price equation was given to us on the previous example. So that price equation is 300 minus x over 30. So 300 minus 4050 over 30 looks like 165. So $165 per paper shredder is going to be what we sell them for. That's the price to sell them for. And so our maximum profit, okay, we want to evaluate our profit equation, add that 4050 as well. So our profit equation, our simplified profit equation is here. Okay, so we're going to have 270 times 4050 minus 4050 squared over 30, and then subtract from that the 90,000. So that looks like it gives us a profit of 456,750. Okay, let's look at this. That's a continuation of the problem about the markers. So this one is saying, suppose that the government decides to tax the company in example 5 at a rate of $2 for each marker they produce. With this additional cost, how many markers should they produce to maximize their profit? Okay, so this problem is basically identical to the one that we did, except what has changed is because the government is taxing the company, they are going to increase, that's going to increase the cost for the marker. So instead of working through this whole thing, I just want to kind of show you the change that occurs with this. Okay, so because, like I said, because there's that $2 additional tax being charged, that's going to change our cost equation. So our original cost equation for this particular problem was 5,000 plus 2x. We're going to have to add to that an additional 2x because it's $2 per item. So it's 2 times x, and that's going to represent the tax. So it's going to change our cost equation from being this in the previous problem to being this, okay? This 5,000 plus 4x is going to be our cost. So that's going to change our profit equation. So our profit equation, we're going to have to make that change here as well for the profit. And then when we take the derivative of it, we're going to see that we actually come up with a slightly different different equation as well. Okay, because once we've combined these together, we have a profit here. Okay, so we'll take the derivative of this, which gives us this. We'll set it equal to 0 and solve, and that will give us our critical number of 3,000. So with the additional taxing that we have and the additional cost incurred there, it changes that number that's going to minimize or maximize it to 3,000. Okay. If you take the second derivative, you end up with a negative second derivative, which means it's opening downward. So it is in fact going to maximize the quantity that we're looking at here. So we know that it does produce a maximum profit when we produce 3,000 items with this. So if we plug 3,000 back into the profit equation, we're going to make $4,000. Okay. And then the price, if we plug the 3,000 back into the price equation, we need to sell those markers for $7 each instead of, I think it was originally $6 that we wanted to sell them for. So you can see that it does change this. Yes, it was an increase of $1 per marker in cost to the consumer because of the tax being incurred as part of the cost for that. So basically, $1 of the $2 tax increase, $1 is getting absorbed by the company. The other dollar is getting passed on to the consumer in that particular situation. Let's look at this problem here. We've got a management training company finds that at a price of $400 per person, 1,000 people will attend their seminar. For each $5 decrease in the price, an additional 20 people will attend. How much do they charge in order to maximize the revenue? So we want to maximize revenue for this particular model here. Okay, so we're going to maximize the revenue. So we need to come up with an equation for the revenue. So basically, the company is going to generate their revenue by charging a per person price, and then we need to multiply it by the number of consumers that they actually have. So I want to set it up as two equations. One is the price and one is the number of consumers or people attending this training session that they're training seminar. So the price is going to be $400, which is what they are generally going to charge. But then for each additional $5 that they decrease the price, an additional $20, 20 people will actually attend. So we're going to say, we're going to let the price be 400 minus 5x. So for every person, for every number additional, for every $5 decrease in price, we're going to get an additional 20 people that will attend. So our number of consumers that we have or people attending this is going to be they expect 1,000 people to attend, but they're going to get an additional 20 people to come for every $5 decrease in price. So we're going to have plus 20x for that. So basically what we're doing is we're going to let x represent the number of price decreases that we have, okay? And that's in $5 increments that we're talking about there. So if we have if x was 1, we'd have one $5 increment. So the price would be $395, and we would expect 1,020 people to attend because of that. So when we let x equal the number of price decreases, then we end up with our price and the number of consumers represented in these two equations here. So our revenue then is going to be the price that we're going to charge times the number of people that are going to attend. And I would say go ahead and multiply this out, like FOIL this out. So 400 times 1,000 is going to be 400,000. Outer is going to be 8,000x. The inner is going to be minus 5,000x, and then the last is going to be minus 100x squared. All right, we've got some like terms we can combine together. These two will combine and give us 3,000x and then minus 100x squared. So that's our revenue equation that we've gotten. Once we get that revenue equation, this problem is just like all the rest. We're going to take the derivative, set it equal to 0, find our critical numbers, and go from there with it. So our first derivative, since we're maximizing revenue, is going to be the derivative of 400,000 is 0. The derivative here is 3,000. The derivative here is minus 200x. We do want to set that equal to 0. So I'll have 3,000 is equal, move the 200 over. We'll divide by 200. And so x is going to be 15. Okay, so we want to have 15 price decreases is basically what we're seeing here. Okay. In order to maximize it. We do need to show that it's a maximum by looking at our second derivative. So the second derivative, this was our first derivative, so the second derivative would just be negative 200. And so that does in fact tell us that we're working with a maximum. And so our maximum revenue itself is, we've got to figure out the price before we can do that. So our price is going to be 400 minus 5 times 15 price decreases. So $325 for the price that we're going to charge. And then our maximum revenue, if we plug that into our revenue equation, if we plug in 15, we're going to have 400,000 plus 3,000 times 15 minus 100 times 15 squared. And so we're going to have $422,500 is going to be our absolute maximum revenue. One thing we do need to keep in mind is that both the price and the number of consumers need to be positive. So we would have 400 minus 5x would be greater than or equal to 0. So that means that 400 is greater than or equal to 5x. And so we've got 80 is greater than or equal to x, or x is less than or equal to 80. So you could have done this as absolute maximums and minimums. Put your critical number of 15. X has to be positive, and then it also has to be less than or equal to 80. So those would be the numbers you would want to check. If you put in 0, you actually get 400,000. You put in 15, you get that 422,500. And if you put in 80, you're going to get 0. Okay, but those would be the critical numbers because these are your endpoints of your interval, and then this would be your critical number here. So price does need to be positive, and your number of price decreases since your equation's in terms of x, so you need to figure out the parameters for x, and so it means that the number of price decreases would also have to be greater than or equal to 0. Okay, on this one here, this one is what would be a good one to practice with too. A walnut grower estimates from past records that if 20 trees are planted per acre, then each tree will average 60 pounds of nuts per year. If for each additional tree planted per acre, the average yield per tree drops 2 pounds, how many trees should be planted to maximize the yield? Okay, so we want to maximize the yield for this particular problem here. Okay, if we want to maximize the yield in this case that we're wanting to maximize is going to come from the number of trees, and we want to multiply the number of trees that's planted times the pounds of nuts per tree. So as more trees are planted, they don't produce as much because they're competing for more things in the ecosystem and so forth in that area. And so it's going to decrease the production for each of those. So if we're starting out and we've got 20 trees, okay, if we increase the number of trees, for every increase in the number of trees, what we're going to see is we're going to see a 2-pound drop per yield for that tree. So normally we would expect about 60, but we're going to lose 2 pounds per tree that's planted. And so that's going to be the yield that we're working with on this one. Okay, so we're going to multiply this out. So we'll have 1200 minus 40x plus 60x minus 2x squared. So 1200 plus 20x minus 2x squared, that's going to represent our total maximum yield per acre there. Okay. All right, so we want to take the derivative of this, so that's going to be 20 minus 4x, and we're going to solve this by setting it equal to 0. Okay, so it looks like x is going to be 5. So basically what we're saying there is that if we plant 5 additional trees, then that's going to give us our maximum yield per acre with the offset that occurs when you plant an additional tree there. So if we look at the second derivative of this, that second derivative would just be -4, and so it is in fact a maximum. And if we want the maximum yield, we're going to plug 5 into this. So that's going to be, if I plug 5 in here, that's going to be 25. And if I plug 5 in, that would be 60 minus 10 would be 50. So our maximum yield, if we multiply 25 times 50, is going to be $1,250, or 1,250, not dollars in this case. That would be 1,250 pounds of nuts per acre is what we would be maximizing. Okay, so our maximum yield is 1,250 pounds per acre when 5 additional trees are planted on each acre. Okay, the last couple examples here are a little bit more straightforward. We want to find the maximum profit and the number of units that must be produced and sold in order to yield the maximum profit. And you're given your revenue and your cost equations. So these would be some good ones to just practice on. We're wanting to maximize, in this case, profit. So we need a profit equation. So our profit is going to be our revenue minus our cost. And we continue to use these formulas, so be sure that you do know them. So our revenue, so we have our revenue here, and we're going to subtract the cost from it. Be sure that you put that cost in parentheses and distribute the negative together. At this point, all I'm doing is simplifying, so I'm going to distribute the negative through, Okay, so that gives us our profit equation. Now I want to combine like terms. So the 40x and the 6x is going to give me 34x minus 0.5x squared minus 30. And now I'll take the derivative because I do want to maximize the profit. So I'm going to take the derivative of the profit. So 34 minus 1x is equal to 0. So if I move that x over, I'm going to get 34 as my critical number. So if I look at the second derivative of this would be -1, and therefore it would be a maximum that I'm working with. So this is going to give me the maximum profit that the maximum profit for this particular situation. So I want to produce 34 units. So I know how many units I want to produce. I don't know the price that I want to sell them for or the maximum profit at this point. It's not asking me for the price, so I can actually just go directly to my profit equation here and plug in 34. So 34 times 34 minus 0.5 times 34 squared minus 30 going to give me 548. And that should be my maximum profit. Okay, so this one, again, we're finding the maximum profit. And okay, so we already have our answer here, but we'll take a look on how we get to that point. Again, these are good problems to practice with. So our profit then is going to be our revenue minus our cost. Okay, so we're going to have 50x minus 0.1x squared minus that cost. So I'll have 50x minus 0.1x squared minus 6x and then minus 15. Okay, so we'll combine some like terms together. We've got a few here. So 44x minus 0.1x squared minus 15. Okay, so that gives us our profit equation. And anytime we see that we want to maximize something, that means we're going to take the derivative of that quantity. So we need to first find that quantity and then take the derivative of it. So the derivative then is going to be, going back to this equation here, we're going to take that derivative. So it's going to be 44 minus 0.2x, because we're going to multiply 2 times 0.1 will give me 0.2x. And then we know that we need to set that derivative equal to 0. All right, so I'm going to move this to the other side and then divide by 0.2. And so I'm going to get x is equal to 220. So we need to produce 220 units. And since it's not asking for the price, I can actually go directly to that profit equation here. So my profit, I'll plug the 220 in, 44 times 220 minus 0.1 times 220 minus 15. And this should be squared. Okay, and that's going to give us 48.25. Right, so that's going to be our maximum profit. And we haven't actually shown that it is truly a maximum. So we do need to look at that second derivative. So our second derivative would be, our first derivative is over here. So our second derivative is going to be negative 0.2. So since it's a negative, it's going to open down. So it would therefore be a maximum. Okay, this one we want to again maximize the profit. So we need a profit equation and take the derivative of it. That's kind of what that wording tells us, is take the derivative of the profit equation. So our profit equation is a little bit more complicated here, but we're still going to do revenue minus cost. So I've got the revenue is this equation, and then the cost is this longer equation here. Okay, so I'm going to distribute. So I'm basically changing the signs of all these terms here. And then I want to see if I can combine some like terms together. So the 6x and the negative 2x will become a 4x. The x squareds will be just positive x squared, have minus x to the third, and then minus 1. And that's going to be my profit equation. So yes, we do have a little bit more complicated profit equation. We're still going to do the same thing we've done before. So we're going to take the derivative of the profit equation because that's what we're wanting to find the maximum of. So that would be 4 plus 2x minus 3x squared. Okay, just like we've done before, we're going to set that equal to 0. And when I'm working with a quadratic, which this one is a quadratic, I do like for my leading coefficient to be 0. I mean, to be positive. So I'm going to move this over to the right so that it is positive, so that 3 is positive. So I'm going to take the 2x over and I'm going to take the 4 over. At this point, I would say see if it factors. I'm going to go ahead and tell you it doesn't factor in this case. So because it doesn't factor, we're going to use the quadratic formula to solve this. Okay, so our quadratic formula is going to be negative b plus or minus the square root of b squared minus 4ac over 2a. So negative 2 plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Keep in mind the a, b, and c are not the variables, they're just the coefficients. So this is a, b, and c. Okay, so we've got 2 plus or minus the square root of 4 plus, looks like 12 times 4 would be 48 over 6. And in this particular class, decimals are fine. Okay. So what I would suggest is just put this in, do one case where you do 2 plus the square root of 52 over 6. And that gives us 1.535. And then if we do 2 minus the square root of 52 over 6, we end up with negative 0.86. Okay, a negative number of units would not make sense. So we're going to disregard that. We're just going to work with the 1.535. And that's going to be the number of units that must be produced and sold in order to yield the maximum profit. Okay. Keep in mind that these it doesn't say it here, but these are in thousands because otherwise it's not going to make sense. Okay, if we look at the second derivative, we're going to have, looking at this, we'll have 2 minus 6x. So if I plug in the 1.535, then I'm going to get a negative. It doesn't really matter what the value is, it's just going to give me a negative. So I know from that that it is in fact a maximum. And if I want the profit itself, I'm going to have to plug in to the profit equation. So my profit equation in its simplest form is here. So I'm going to take that equation and plug in the 1.535. Okay, and then evaluate that. And so when I evaluate that, I'm going to get 3.879. And since it's in thousands, that's going to be 3,879 units is what I'm looking at there. Okay, last example. Rags, a clothing firm determines that in order to sell X suits, the price per suit must be P equals 160 minus 0.5, and this should be an X here. It also determines that the total cost of producing X suits is given by this cost equation. So A, we want to find our revenue function. So our revenue is X times the price. So that's going to be 160 minus 0.5X. And we'll go ahead and simplify that down. All right, so that would be our revenue function. Our profit function, then we know, is revenue minus cost. So our revenue we just found to be this equation. We're going to take away the cost function, which is what was given to us. All right, we'll distribute the negative throughout. And then we'll combine some like terms together. So we've got 160x minus 0.5x. Okay, so we do want to combine these two together. And so if I combine those together, I'll have negative 1.25x squared and then minus the 5,000. Okay, so how many suits must the company produce and sell in order to maximize the profit? Okay, so we just found that our profit equation is 160x minus 1.25x squared minus 5,000. So if we're going to maximize the profit, we need to take the derivative of the profit. So that would be 160 minus 2.5x, and we need to set that equal to 0. So 160, I'll move the 2.5 to the right, divide by the 2.5. So x is going to be, it's like 64 suits. I do need to check and make sure that it is in fact a maximum, and so my second derivative is negative 2.5, it's less than 0, so it is a maximum. Okay, so we would produce 64 suits in order to maximize the profit. So the actual maximum profit is going to be plugging the 64 into the profit equation. And so that gives us $120 would be the maximum profit for this scenario. And then finally, the price that needs to be charged in order to maximize the profit. We're going to go back to our price equation to do that. So 160 minus 0.5, remember that had an X beside of it. So times 64 is going to be $128, and that would be per suit. And while this doesn't look like a very profitable company, mathematically that is correct, and that's what the scenario indicates for that particular situation.